Good morning, everyone. So let's start the today's class. So today we are going to discuss again an important topic of class 12 standard, that magnetic section, magnetic effect of current, earth magnetism, electromagnetic induction, and alternating current. So we can say that bunches of topics that I am going to cover on today class are a quick closure of all the topics. The first topic, as you seen in magnetic effect of current, and then magnetism and matter, EMI and alternating current. So firstly, if you want to start our magnetic section, so we have got thought process how whole magnetic section will run. Okay, that governed by one basic law, that is the Biot-Savart law. So we have to firstly understanding of the Biot-Savart law. That law describes for a small elemental current carrying wire. If small element, we can say the differential element hai length d, and the current carrying this DL element is I. Okay, then what is the magnetic field at any distance r? This is the vector form of the Biot-Savart law because of small element. Sometimes in the problem, it is asked about what is the magnitude form of the Biot-Savart law. Because we already know that whenever a vector quantity will come, we decide the direction by using right hand thumb rule or right hand palm rule. And on the behalf, when we want to describe the magnitude, for magnitude, we can write down this mu naught I dl sine theta divide over r square, where theta is the angle between the this position vector and dl vector. This is very, very important, beta. This is the magnitude form of the Biot-Savart law. And what is the whatever the derivations that perform on the later, that is application of Biot-Savart law. The first application, that magnetic field due to straight wire. Okay. So what is the magnetic field due to straight wire? That first of all, we consider a wire having current I. This is the finite wire. We can say the end is defined. Okay. In order to write down the magnetic field at any distance P, first of all, we have to draw a perpendicular distance from this wire. This is very, very important. Suppose this distance is R. Then we have to join the end point at this point P. Yes, sir. We can join this and see this angle is, if theta 1 and this angle is theta 2, the magnetic field is written in this manner at point B. Mu naught upon 4 pi I upon R sine theta 1 plus sine theta 2. One thing we have to also focus here, beta, from the perpendicular line, theta 1 is going in this sense and theta 2 is opposite sense. See, if theta 1 is in clockwise sense, then theta 2 is anti-clockwise sense, then we have to use this formula. If both the theta 1 and theta 2 in the same sense, then we have to put negative sign here. This is the important crunch point of this particular formula, and this formula is the again very, very useful, as similar to electrostatics. Okay, beta. What about direction? Just using the right hand thumb rule, place your right hand finger in the direction of current and curl your finger where you have to find out the field. The thumb represents the direction of magnetic field. I hope this is clear for everyone. I hope this is clear. Yes. So guys, how we can apply this formula? Sir, if suppose that theta 1 and theta 2 will become 90 degree, when this will become 90 degree, when we take infinite length of wire, right? In this case, we can say that this theta 1 will become 90, this theta 2 will become 90, and if we put sine 90 plus sine 90, this will become 2. And the very, very important formula, beta, that magnetic field due to infinite straight wire, that is the very, very important formula. Again, I am saying that mu naught I upon 2 pi r. And This formula we can say this must be on our tip. And what is the graph of magnetic field versus distance beta? We can say again this is a rectangular hyperbola. I hope this is clear for everyone. Okay. And what is the direction? What is the direction? If the current is flowing in this direction, we can say magnetic field at this point convert to plane of paper by using right hand thumb rule. I hope this is clear for everyone. If you want to application of this type of formula, yes sir. Suppose this is an infinite wire having current I, and this is again an infinite wire having current I. Okay, what is the magnetic field at midpoint? Exact midpoint between two wires. How we can find out? Due to first wire, what is the direction beta? Inward, inward. And what is the magnitude? Mu naught I upon 2 pi r. If this is the midpoint, then distance is r, and this distance is also equal to r. At the similar manner, we can say V1 is inside to plane of paper. What about magnetic field due to wire 2? We can say, sir, this is the outward to plane of paper. Current is exactly same. Distance is exactly same. So we can say V1 and V2 is equal in magnitude but opposite in direction. Then what about net magnetic field at this point, beta? Anybody in this class, beta? V1 is cross and V2 is dot. One is the inside to plane of board and another is the outside to plane of board. We can say net field equal to 0. Such type of questions are formed. So we have to mentally prepare for that. Right, beta? Let's move for the next slide. That firstly we have to straight wire. Then we have to curl this wire in the circular form. Okay. If we change the orientation of the wire, then the magnetic field created by that wire in the surrounding is also going to be changed. We have to keep in mind this thing. Sir, this is also depend upon the orientation of the wire, how wire is formed, how wire is wired. So this is the magnetic field due to circular loop, right? In the circular loop, sometimes we also given some number of terms. So we can say in this case, mu naught Ni upon 2r. What is important in this formula? Firstly, again, V is inversely proportional to 1 upon r. We can say if loop is larger radius, then magnetic field at center it will decrease. Okay, and this is directly proportional to number of turn. This is directly proportional to number of turn. So again, we have to. This is the very we can say you can easily score in this topic, beta, because the whole chapter is based on the formula. Okay, just write the formula, remember the formula, make a short notes, and again revise. Like as a medicine, we can say what is the beta magnetic field at the axis. Suppose this is our coil having current I, and if we want to find out the magnetic field at some axial point X, and the coil is having radius R, something like this situation. I hope this is clear. And we know that we are already aware about this formula because we just come out from the examination. Okay. After 12th, we can say this formula is the very important, and mu naught Ni r square 2 times r square x square power 3 by 2. Beta, what is important in this formula? If we put x equal to 0 here, we can say we will reach at center. If we put x equal to 0 here, we will get this formula. So we can remember this formula also. Okay. And in this formula, beta, what is the variation of magnetic field for the coil? We have to see the graph also, beta. Yes, Anu. We know that at center the magnetic field value is maximum, and here this value will become 1 upon infinite, v tending to 0. So we can say that at distance is positive infinite, the magnetic field is 0. At distance is negative infinite, this again equal to 0. And at center it is maximum. So if we join this with the help of a curve, this is something like this. This is something like this. This graph is either upward or downward depending upon the direction of magnetic field, either rightward or leftward. I hope this is clear. This is the variation of magnetic field versus distance for a coil. I hope this is clear. Let's move for magnetic field due to solenoid. Sir, what is the solenoid? Solenoid is nothing but beta something. Suppose that this is the pen, and if you make a conducting coil around this pen, this is known as the solenoid. This is known as the solenoid. So in the solenoid, what is the formula? Actually, in our syllabus, only the infinite length solenoid. That length is much larger than the radius of solenoid. Okay, this length is much larger than the radius of solenoid, and this formula equal to mu naught n I. Sir, what is important in this formula? Because sometimes student can't remember what is the n. N is the number of length, number of turn per unit length, number of turn per unit length. This is again important, and this is given for if the solenoid is finite length. Say this end makes theta 1 angle and this end makes theta 2 angle from this axis. Okay, so this is the formula that is, I think this is useful for your advanced purpose. Mu naught ni by 2 cos theta 1 minus cos theta 2. Okay, again if you want to make infinite solenoid, and we can put the value beta theta 1 equal to here, it is very long. So we can say here theta 1 equal to 0 and theta 2 equal to 180 degree. If we put this value here, we will get this formula. I hope this is helpful for you, how we can apply this. Okay, beta, magnetic field due to solenoid. One another form, beta, if this is a rod and that is the flexible rod, and this rod we can turn in a form of coil, like a donut, So this type of shape is known as the beta toroid. This type of shape is known as the beta toroid. And sometimes it is also asked beta what is magnetic field due to toroid at the center. Is this clear beta? Yes or no? Outside magnetic field is always zero, either due to solenoid, Only the field we are getting inside the solenoid or inside the toroid. This is remember, you have to remember this. Okay beta, and more and less we consider the field is constant along the length. This field is constant because this is independent of the distance. For the toroid, we are not going to change nothing, but we have to write down mu naught n I. What is n here? We again say number of turn per unit length. What is length here? That is the circumference of the circle. This will become mu naught n I upon 2 pi r. One thing we have to remember, beta, r is the mean radius. R is the mean radius because if we consider thickness too much small, so sometimes if inner and outer radius is given, we have to consider mean radius here. Okay, I hope this is clear. Next one is the Ampere's law. Beta. What is the Ampere's law? Ampere's is just an analogy, similar type of Gauss. In electrostatics, whatever importance of the Gauss law. Yeah, Ganesh. Yeah, I will consider that case. That is happen for a solid cylinder. Okay. Next, I will consider that case. Okay. Ampere's law. What is the Ampere's law? Sir, Ampere's law just similar type of Gauss law in magnetic field. Okay. What is the Gauss law? Sir, Gauss law is E dot ds and close integral that q enclosed upon epsilon naught. In the same similarity. Hello. हाँ सर नहीं जा रहा है अभी, तो ट्राई तो किया हूँ, अभी पता नहीं है कि नहीं वहां पे। सर इधर से करता हूँ। हाँ, अच्छे से बात किया था, वो भी बोल रहे थे कि ऐसा ऐसा बोले कि कल लोग किया था, नहीं हो रहा है बट। ये अवंती लाइव वन में। हम्म। वेट फॉर 2 मिनट। पासवर्ड वही ऑनती फेलोज@2023। फिर शेड्यूल टू किया हूँ इसमें। हाँ, गो लाइव का बटन नहीं आ रहा है ऐसे। हाँ हाँ सर, उसमें नहीं आ रहा था, फिर मैंने अभी तुरंत दूसरी स्ट्रीम क्रिएट करके डाला उसमें, शायद उसमें आ जाए। हाँ, अभी अभी डाला उसको। ये यार सही है। हाँ हाँ सर, अभी अभी मैंने किया है, थोड़ा क्लास के बाद फिर मैं डिस्कस भी करूंगा आपसे, थोड़ा सा इशू हो रहा है इस पे। तो मैं कंटिन्यू करता हूँ क्लास। ओके बेटा, लेट्स कंटिन्यू। सॉरी फॉर interruption. Sir, Ampere's law B dot dl equal to mu naught I. Okay. In the place of charge, we have to put the current. And here we can say a similarity. By similarity, in the place of electric field, magnetic field is here. And this is work on a, this we can say B dot dl, something like a term is known as line integral. This is helpful for a mathematics student. Sir, B dot dl is how we can say this term is known as the line integral. Okay, beta. So we can say line integral along a closed loop is equal to mu naught I in closed. So here one thing we have to keep in mind, B is due to the wire present inside and outside the Ampere loop. This loop is known as the Amperian loop. So B is due to all the current carrying wire, either it present inside the loop, either it outside the loop. But I enclosed suggests that we have to consider only those current which lie inside the Amperian loop. Okay, and the very important next slide we can say what is the magnetic field due to long cylindrical cell. This is the application of the Ampere's law. How we can say, sir, if this is the cell, so we can consider that there is no current inside the cell and the current present only along the circumference. I hope this is clear, because hollow type of cell. So what is the magnetic field that R less than capital R? So this is just behaving like as a infinite wire. Because if somebody see this wire at a large distance, this is behaving like as an infinite wire. So we can say, we can directly put this formula. I hope this is clear. And the second one, what is the magnetic field inside inside the cell? Because inside the cell there is no current. If there is no current, then B equal to 0. I hope, Ganesh, this will clear. Okay. The next I want to discuss here, beta, what happens if we consider a solid wire, infinite solid wire. Yes, Anu? Infinite solid wire, it means the current is present inside this cylinder, and the whole current we can say I enclosed. So what is the value of magnetic field at point P? Sir, this is behaving like as an infinite wire. So we can say mu naught I upon 2 pi r. I hope this is clear. This is the magnetic field R greater than R. But what about beta R less than R? Because current is present in each branch. Yes or no? This is very important formula beta. Listen, mu naught current density and the distance r. Suppose if we cut a small part at a distance r here, yes, yeah, mu naught j r divide over 2. This is the formula inside the solid cylinder. Note down this formula beta. Inside the solid cylinder, this is the formula, and j is the current density. And current density we can say total I upon total area into r. In this formula, what we can say that B is directly proportional to r. B is directly proportional to R. There is no need to note down any formula because we will provide all the material in the form of PDF. So there is no worry about the note down. Only you have to understand the concept. I hope this is clear. That B is proportional to R. Then what is the variation beta for solid cylinder? If you want to draw the graph beta, is sir, this is the distance R equal to R till surface, and this is distance that beyond the surface. We can say this is the straight line relationship with small r, B is proportional to R. So this is something like this. And beyond the capital R, we can say that the B is inversely proportional to 1 upon R. So I think this is clear for everyone. This is very important formula. Okay, beta. As similar to electrostatic, that we can say non-conducting solid sphere. Oh, let's move for the magnetic force. What is magnetic force beta? Magnetic force acting on a moving point charge. Magnetic force acting on a moving point charge beta, that is given F equal to QB cross B. Again, this formula tells something here. The magnetic force that is perpendicular to velocity and perpendicular to magnetic field by the property of cross product. One thing also we observe here beta, if force is perpendicular to velocity, so we can say what about the power? What about the power beta? Power can define that the force dot velocity, and if two vectors perpendicular to each other, their dot product will 0, so we can say power equal to 0. If power equal to 0 here, we can say what about the work done? There is no work done. There is no work done by the charge particle in the uniform magnetic field. I hope this is clear. This type of question, that one-liner question, is always asked, sir, what is the power due to, what is the work done due to charge particle in magnetic field? What is your answer beta? 0, because force is perpendicular to velocity at any instant beta, at any instant and all the path. Okay, and this is the special case beta when r velocity and magnetic field is perpendicular to each other. So we can say the radius of the path is circular and the track of radius is mb upon qb. Again, this is the very important formula. We have to keep in mind the circular path performed by a charged particle whenever it is projected perpendicular to magnetic field B. And we know that sir, mb is nothing but this is the momentum. So we can say p upon qb. What is the momentum in the form of kinetic energy? Sir, we know that under root 2 mk. So we can say that this will become under root 2 mk upon qb. I hope this is clear. Sir, what is the k? What is the k? K is the kinetic energy of the charged particle. Kinetic energy, we know from electrostatics, kinetic energy always written charge into potential difference. So this can be written as charge into potential difference V divide over QB. Yes or no, beta? Very good, Vinesh. Yes or no? So, sir, there are 4 variety of formula, and question will ask, if in question velocity is constant, then we are going to use this formula. If momentum is constant, then we are going to use this formula. If kinetic energy is constant, then third formula. If potential is constant, then fourth formula. I hope this is clear. Which type of question is asked? Find the ratio of alpha particle and the proton and triton and helium. Such type of question is asked, and we have to mentally prepare which parameter is going to be set the constant value. Okay, then we use to do that type of formula. Next one is the same type of relation is the time period 2 pi m upon qb. Only we have to see the which one is the proportionality and what is the nature, that direct or inverse we can get right answer for a given question. I hope this is clear. The second case, whenever velocity and magnetic field make some angle, yes or no? If angle is 0, then straight line path. If angle is 90, then circular path. If makes some angle, then we can say it will also move in forward direction. It also move in circular path. Then such type of path that is known as the helical path. Such type of path that is known as the helical path, beta. Yes, Yanu. Yes, Yanu. I hope this is clear. Very good, Rajesh. Yeah. Marvelous task, beta. We can say this is path that is performed by charge particle, helical या helix. Spring coil, helix. Yes, Yanu, beta. So we can see, sir, what is the time period, because it is also perform circular motion 2 pi m upon qb. Radius is this, which is nothing but distance between two coil. Distance between two coil. So we can say that is time into horizontal velocity. That v cos theta is the horizontal velocity and time is this. This is the page. Next, if both electric field and magnetic field is present, then this force is known as the Lorentz force. This force is known as the beta Lorentz force. We have to keep in mind, and that is the summation of the two force. Okay. And next one is the magnetic force on a current conducting wire. Magnetic force on a current conducting wire. F equal to I L cross B. L is the vector quantity. Small dl vector. We can say this formula is written as df equal to I dl cross B. Beta, one thing we have to note down here, dl is a differential vector, length vector. Okay. If this vector, because this is the vector quantity, if we form a closed coil, then what is the value of dl vector? Dl is vector. If we form a coil, then initial and final point will become same. Then this dl will become 0. Then the force value will become 0. So we can say if a closed coil loop, that will present in a uniform magnetic field, then the value of force is 0. Again, this is important. And next one is the magnetic moment of a current carrying coil. We can say this is NIA. This is defined as current into area, where area is a vector. The direction of magnetic moment in the direction of area vector. What is the torque? Just similar to electrostatics, tau m cross v, where p cross e. This is the single pole. This is the similar to beta magnetic field due to single pole. Magnetic field at axial point. This is just similar to beta dipole. Yes, Yanu? That is the Kp upon 2r cube. So similar mu naught upon 4 pi 2m upon r cube. At the equatorial point, that m upon r cube, where m is the magnetic moment. And magnetic moment for a magnet, that is written as pole strength into distance between pole. Suppose if this is a magnet, this is north pole, south pole, and this distance is d, and we can say m is the pole strength that is given for each magnet. North pole is behaving like as a positive charge, south pole is behaving like as a negative charge. I hope this is clear. We can just make an analogy with electrostatics. Okay, beta. Let's move for magnetic flux. Let's start the magnetic flux. Before going to start the magnetic flux, I want to tell you something in earth magnetism section, beta. In earth magnetism, whatever important parameter we have to keep in mind. One is the deep angle. What is the deep angle, beta? Suppose the earth magnetic field is oriented in this direction, and this is the horizontal axis. Whatever angle made by the net magnetic field from the horizontal direction, that angle is known as the deep angle. Okay, beta, and this is the vertical. So we can say here BH always written as net magnetic field into cos theta. B vertical is written as B sin theta. Yes, Yano, beta. What is the deep angle? That is the horizontal angle. Angle made by net magnetic field from the horizontal. Yes, Yano, beta. This is the important term we have to keep in mind. The next is the beta. What is the declination angle? What is the declination angle? To declination angle, we can say, suppose that if this is our earth and this is the geographical north, this is the geographical south, and suppose if we consider a plane passing through this point, and we know that our magnetic north and magnetic south, that is something orientated with some angle, that is 11.3 degree angle. Okay, beta. And we can say if we consider a plane passing through this point, then the angle made by two plane, that one plane in the magnetic meridian and another plane in the geographical meridian, the angle between two plane is known as the declination angle, and the magnetic field always lie in the magnetic meridian. This thing we have to keep in mind. Such type of question is generally asked. What is the horizontal component, vertical component, and one thing we also know what is one Gauss. One Gauss equal to 10 raised to power minus 4 Tesla. Okay, beta. And another is the property of material, that paramagnetic, diamagnetic, ferromagnetic. So one thing we have to know, beta. If we talk about the diamagnetic material, if we talk about para and ferromagnetic material. So here one thing is defined as susceptibility. Susceptibility means, beta, ease of magnetization. Which material want to magnetize, which material more want to magnetize. So we can say here susceptibility, that is represented by a letter psi, that is mu r minus 1. Okay, beta. Diamagnetic material repel, paramagnetic material small repulsion, and the ferromagnetic material attract magnetic field line. So we can say that if we have a, suppose we have a current carrying coil, and this is the magnetic field, and magnetic field away from this point, we can say this is the dia. If magnetic field towards small repulsion but not get inside the coil, this is the para. If magnetic field passing through this coil, we can say this type of material is known as the ferromagnetic. In the ferromagnetic material, the domains are present, and we can say if we apply the external magnetic field, they will create a large, huge magnetization effect. So we have to keep in mind that it's the such type of property, and we have to also quick closure of the NCRT in this type of chapters. Okay, because earth magnetism is the very important, and last recent 3 to 4 years the question will come in this section. What is the para, dia, ferro? What is the high hysteresis loop? What is the energy loss in a high hysteresis loop? So we have to keep in mind such type of thing. Let's move for the next, beta. That is the magnetic flux. Magnetic flux, beta, that can be written as the electric flux B dot area vector, and we know that here ds is the area vector. Don't confuse, because ds is the plane, ds is the area vector. We can say this we can written as bs cos theta. I hope this is clear. This is the Faraday law. E equal to minus d phi upon dt. One is the Lenz law, that described about the direction of the, that what is the direction of the induced EMF. Yeah, induced current. I hope this is clear. If the coil is closed, then current is induced. So we can say this is described, negative sign described about the Lenz law, and the magnitude that can be written as beta d phi upon dt. And we know phi is the magnetic flux, that is the B dot A. That is the B dot A. This such type of questions are from the magnetic field is given in the time function, variable function, and we have to calculate the EMF of given time. Yeah, we have to prepare for this. One is the beta induced EMF due to rotation. Suppose we have a rod, and the rod is hinged at this point, and we rotate the rod with some angular velocity omega, and say the length of rod is L. Then what is the EMF generated between the hinge point and the free point, beta? Say this is the point O and this is the point A. This voltage or EMF generated between the hinge point and free point of rod, we have to keep in mind half B omega L square. Yes, this type of formula we have to keep in mind. One is the, this is the application of the Faraday law. Again, we can say that here if the area is changing, suppose we have a loop and loop area is continuously decreased with time. Okay, then such type of question is also done by this formula. We have to put area pi r square, and if magnetic field is constant, take outside the differentiation and make a differentiation of the radius. Such type of question we have to keep in mind. And one thing that in the electromagnetic section, whatever electric field is induced, that is non-conservative in nature. Non-conservative in nature, so we can say that the induced electric field is non-conservative in nature. Energy is not conserved in this field, and that form a losses in the form of eddy currents, small cuts. Okay, beta. This is the important thing we have to keep in mind. This is the non-conservative in nature. Next, what is the self-induction? This is self-induction. We know that in a coil, if V number of turn is present, then phi is proportional to I beta, and we can say a proportionality constant that L. We know that the magnetic field is always proportional to I in each and every formula in the magnetic section. So we can say that flux is also proportional to B. So flux is proportional to I. That is the inherent property, that is the flux is proportional to, directly proportional to current, and here a constant comes, that L is the self inductance of the coil. And if we put this value in the formula of the Faraday law, d phi upon dt, so this will become this formula. I hope this is clear. Okay. And the self inductance of the solenoid, we have to keep in mind what is the proportionality of N. We can say this is the mu naught N square pi R square L, and we can say this is the area and this is the length. Inductor is represented by in this way, and the similar type of, we can say if current is increases here, di upon dt, that can be say that the rate change of current, So we can say also similar type of resistance property. If current is flowing in this direction, this point is A, this point is B, here the similar type of property we can say that. What is the energy stored? Like as a capacitor half CV square, here energy is stored half Li square. So this is the formula of the LR circuit, that is the growth half current. It is just similar to in capacitor RC circuit, that is the charge. Just similar formula, that the growth of the charge. So I equal to, we can say this value is known as the I maximum 1 minus e raised to power RT upon L. RT upon L. Okay, beta. Let's move further. Let's move for the graph. This graph is increasing, so we can say after some time it will get saturated, and the maximum value is E upon R. And one time constant, the value will become 63% of final current. So we have to keep in mind such type of thing. The similar type of graph, just opposite in nature, that is the decaying current. So we can say in the decaying current, that is the exponential decreasing function. In this case, this is the exponential decreasing function, such type of graph. And here the time constant is the initial value of this current. What is the mutual inductance? Just similar to self inductance, the formula is also here. And the series and parallel combination of the inductance is beta just similar to resistor. We have to keep in mind. And one is the sometime asked what is the coupling constant here? What is the coupling constant here? That is written as M equal to K root over L1 L2. Such type of formula because JEE main asks in similar type of questions. Okay. One is the most important topic we can say, that is the transformer. Okay, beta. In transformer, that is the primary side, this is the secondary side, and we know this work on the EMI, electromagnetic induction. The ratio we have to keep in mind is the EMF in the secondary divide over primary, NS upon NP and IP upon S. Okay, the efficiency is given at 100%. Then we can say if efficiency is given 100%, then we can use the formula. This formula is also equal to this because of the efficiency. If there is some losses are present, suppose 80%, 70%, then we have to use the formula by using consider the loss. Because we know that P equal to V into I, power output is 80% of the input, we can use similar type of concept. LC oscillation, we have to remember the frequency of the LC oscillation, that omega equal to root over LC. Okay, better that depend upon L and C and which type of nature that will govern. Let's move further. AC section. We know what is the meaning of alternate, that current change its direction with time. So we can say this is the DC, this is the also DC because this is not changing its direction. Direction change means it also go in negative direction. These are the types of AC. Whenever here we more interested in the root mean value. So here root mean value, how we can calculate the root mean value? This is given in a particular manner, that V RMS, we can say that V1 square, V2 square, V3 square, that is square, mean and average. This is the root mean value. And for the continuous, how we can calculate the RMS value beta? We have to also remember this. Suppose if a continuous function is given, then we can say that RMS value is completed in this manner, V RMS square dt and divide over dt. 0 to t, 0 to t. We have to find out the function at the function of time. VRMS is the function of time, then put the value and we will get VRMS value. What is the power factor, beta? Power factor, that is the cos phi, and cos phi is R upon Z. So let's talk about what is the wattless current, that I am sin phi. This is known as the wattless current. We know that R is the resistance, XL is the inductive resistance, X is the capacitive resistance, and what is L, what is C, we already know, beta. Okay, so this type of XL is known as the beta. This type of known as resistance in the across inductor, that is known as the inductive reactance. This is known as the capacitive reactance. I hope this is clear. And we have to also know this formula, sir. XL is always written as omega L. So we can say what is the graph between XL versus omega or frequency, that is the straight line. At the same time, Fc equal to 1 upon omega C. So what is the graph, beta? 2 pi f upon Fc. That is again rectangular hyperbola. In the pure case of the pure resistive circuit, that is the power just similar to DC. Just similar to DC. Yeah, wattless current. In the case of wattless current, that it depend upon the phase difference, beta. If cos phi, because we know that what is our phase, what is our beta wattless current, as we discussed in the previous slide. Wattless current, we can say our wattless current is written as I am sin phi. Sin phi is the phase angle. Okay, if phase angle is 0, in the case of pure resistive circuit, we can say phase angle is 0. We can say that is the wattless current. Okay, so we have to keep in mind. And the pure capacitor, pure inductive circuit, we know that in the case of the pure capacitive circuit, current will read by 90° with voltage. In the vice and versa in the case of the pure inductive circuit. Okay, because here the phase angle is 90°, so we can say in the case of the average power is 0. Let's solve some problems, beta. Let's solve this problem. What is given? An electron is moving plus x direction with the velocity is given this, and it is saying that the direction of magnetic field set up in the region such that electron keep moving along positive x direction. What is the meaning of this, beta? Electron will not change its direction of motion. It means there is no force experienced by electron. There is only two possibility of force. One is the electrostatic force, because electric field is given, and another is the magnetic. Okay, because it is given that electron is moving in plus x direction, velocity is along plus x direction, and electric field is applied plus y direction. So this is the direction of the electric field. I hope this is clear. Okay. And if electron, we have to keep in mind, electron not a positive charge. If electron is moving in this direction, the force experienced by electron in which direction? Sir, if this is a positive charge, then the force in the direction of electric field. This is a negative charge. We can say electric force act in the downward direction, and the magnitude, that is the Q into E. I hope this is clear. And the charge of electron. I hope this is clear. If we counterbalance this force, then we must apply a magnetic force in plus y direction, so that electron continuously moving without deflection. So we have to say that for the counterbalance of this electric force, we have to apply a magnetic force in this direction. So we have to choose a magnetic field in this direction, so that magnetic field upward in y direction. Okay, beta. Then what is the possible direction of magnetic field? Anybody, beta? What is the possible direction of magnetic field? Sir, V cross V. If V is in this direction, and if we consider the positive charge, then what if we consider magnetic field in the z direction? Then the direction of beta, then the direction of force in negative y direction. In the case of positive charge, if in the place of positive charge we consider negative charge, then it will become positive y direction. We can say what is the direction of magnetic field? That answer is the plus z direction. Okay, we can say plus z direction is clear. For the magnitude, we can say EV equal to QVB. QVB. E and cancel out. We can say the value of B equal to beta E upon V. If we solve this value by putting the data, we can say each given here in the problem that 300 volt per centimeter convert into meter, beta. Convert into meter. So we can say if you convert into meter, this value will become 10 raised to power minus 2. Okay, and what is the velocity given? 6 into 10 raised to power 6. If we solve this, we will get right answer, that is the C. This is clear for everyone, beta. What is the approach? Firstly, we decide the direction by counterbalancing of the force. Then think about the magnitude, balance those force. I hope this is clear. Let's solve the next problem, beta. We select such type of some important problems. That type of problems have most probable to ask in your JEE examination. Okay, here the charge is given, velocity is given, and external field is also given, and it is saying that the force is this one, force is this one. So what is the basic formula, beta? F equal to q v cross b. I hope this is clear. Okay, we just find out the cross product here because velocity and magnetic field is given. And if we find out the velocity vector and magnetic field vector, what is the cross product? I hope everybody know. Everybody know. Yes or no? Everybody know this. Yeah, you can see this in previous slide. You can see this. If any doubt, you can ask. Okay, beta. You can solve here. We can solve here. We will get this value, and we decide the direction by using the right hand thumb rule where magnetic field we have to set. Okay, I hope this is clear. Okay, beta. Let's move for the next. Sir, what is the answer here? This is homework problem for you guys. Just find out the B cross B vector here and put the value of charge, and the by similarity we will get answer. Okay, and this is homework problem for you guys. You can solve this. This again the very important article. Such type of problems is asked again and again. What we have to do? What we have to do such type of problem? Okay, beta. Yeah. What we have to do such type of problem? Anybody? What we have to do such type of problem? Take a screenshot. What we have to do such type of problem, beta? Sir. In this type of problem, that velocity and magnetic field perpendicular to each other, they track on a circular path. And sir, it is saying that the accelerated from rest and the potential difference is given. Then which type of formula we are going to use? R equal to under root 2m q into potential difference divide over qb. I hope this is clear for everyone. Very good, beta. We know that this type of format we have to choose in. Why this type of format? Because potential is given. That 4 type of formula. R equal to mv by qb, p upon qb under root 2m t upon qb under root 2m q upon qb, because potential is present here. B is constant, 2 is constant. We can say here we can say R is proportional, beta. See here, beta, under root m upon q, under root m upon q. So if you want to radius rp upon r alpha, we can say that this will become mp upon m alpha into beta q alpha upon qp. And we know that beta what beta is for proton that is the 1h1, for the alpha that is nothing but helium nucleus 2he4. So that is, we can say mass of alpha is the 4 times of mass of proton, and charge, if we talk of the charge of alpha equal to 2 times charge of proton. I hope this is clear for everyone. Okay, beta. After solving it, you will get answer. I hope answer is A. Okay. Let's move for the next slide, beta. Again, this question is saying that the magnitude of the magnetic field at the center of the hexagonal shape of the coil. The side is given that. So we can say, sir, this is a hexagonal shape. Yes. And suppose if we consider any direction of current, either clock or anti-clockwise, we have to find out the magnetic field at center. Actually, this is the application of the finite wire current element. We can say if we find out magnetic field due to this segment AB, the magnetic field due to all the segment that is acting in the same direction. I hope this is clear inward. So we can say what is the angle made by the hexagonal at the center? We can say, sir, this angle is the 60 degree. So this will become 30, this will become 30, and this is like this. This is like this. This angle theta 130, theta 230, and this current is I. What is the beta? What is the magnetic field? Mu naught upon 4 pi I upon R. Sir, if this side is A, this side, what is the this side, beta? This side will become root 3 by 2A. Because we know that this angle is 30 degree, this side is a by 2. We can say this perpendicular distance, we can say r equal to root 3 by 2a. Correct? Into sine 30 plus sine 30. We know sine 30 is 1 by 2, 1 by 2. This will become 1. This will become mu naught I upon 4 pi root 3a. This is magnetic field due to one straight wire. And there are total 6. There are total 6. And all magnetic field created by all the small finite wire acting in the same direction, we have to multiply by 6. Number of turns is also given. We have to also multiply by number of turns, right? And here the side is given 10 centimeter. If we put all the value 2 mu naught I, that will 6 into 50 divide over 4 pi root 3. What is the value of a beta? 10 centimeter. That will say that weight 10 centimeter means we can say 10 raised to power minus 1 meter. If we solve this beta, we will get answer here mu naught I upon pi, mu naught I upon pi. What is this value? You can easily solve here, and I hope this is clear for everyone. This value will equal to 500 root 3. After calculating this, we will can say that this value will equal to 500 root 3. I hope this is clear for everyone. There is a simple calculation, and this is the concept. Such type of question is also asked. A square coil is given and we have to calculate the magnetic field at center. What we have to do? We have to find out the magnetic field due to one finite wire and multiply by 4. I hope this is clear. Let's solve the next problem. In this problem, beta, this is and circular arc is given having a current I. What is the value of magnetic field at center? If it is subtended at angle theta, then the formula is at center beta mu naught upon, listen formula carefully, mu naught I upon 2r into theta upon 2 pi. This is the formula at center. This is formula at center. One thing we have to keep in mind, theta always put in radian. Theta always put in radian. I hope this is clear. And we can say this is the smaller root. If this angle is 90, then what is this angle? We can say 2 pi minus 90, 3 pi by 2. If this angle is 60 degree, then what is this angle beta? This angle we can say here the angle theta A is 3 pi by 2 and angle theta B that 2 pi minus pi by 3, and this will equal to 5 pi by 3. And just use this formula, we can say P is, because radius is also given 2 centimeter, 4 centimeter. V is proportional to I upon R into theta. If we want to find out beta V1 upon V2, so what we can say? This is I1 upon I2, R2 upon R1, and theta 1 upon theta 2. Put this value and we will get answer. One having radius 2 centimeter, another having radius 4 centimeter. Current is 2 ampere, another is current 3 ampere. Put the value of I1, that is the 2 ampere. 3 ampere, 4 centimeter, 2 centimeter, and this value. We can say what is the ratio of I1 upon I2. We put that 2 upon 3, 4 upon 2, theta 1 upon theta 2. Theta 1, that is the 3 pi by 2 divide over 5 pi by 3. I hope this is clear for everyone. Okay, beta. If we solve this value, we can say this will become 2 into 4 into 3 and 3 divide over 3 into 2 into 5, and after solving it we can get the answer at 6 ratio 5. So this is the application of concept whatever I learned today. Okay, let's move for the next problem beta. The next problem that is based on the concept of the torque, and we know that torque is M cross B. Torque is M cross B. So firstly, we have to find out the magnetic moment, that is I into A. Okay, if the magnetic moment and magnetic field perpendicular to each other, then we can say this formula will become IAB. IAB. I hope this is clear. Okay, and what is the magnetic field here? Magnetic field due to infinite wire. We also know mu naught I upon 2 pi r. So there are some homework problem that I will attach in this slide. We have to solve the problem and you have to tell the answer in the WhatsApp group. Okay, in personal test you can test me, whatever answer you will get. These are some important question I will attach. These are the homework problem for you, and definitely I hope you will share the answer with me. Okay, beta. So thank you so much for class. Let's meet.